In the previous videos, I introduced a few terms that we haven't defined. So now that we have the tools, we're able to formally define them. So we're going to define, for example, the terms model and the term logically valid formulae, or simply to be a valid formulae, which I've used in previous videos. So we define a model in the following way. If the interpretation of a formula is true for a particular interpretation D, then that interpretation is said to be a model of the well-formed formula A, and we denote this in the following way. So we use this symbol called the model symbol with the subscript D for this particular interpretation for A to say that this particular interpretation is a model for A. So the definition of model is talking about a particular interpretation modeling a well-formed formula A, and a particular interpretation D of a well-formed formula A is a model for that well-formed formula A if it makes it true. So for example, in our previous video, our specific model, our specific interpretation with domain D and translator M for this well-formed formula for all x, phi x, y was true. So in this case, this interpretation is a model of this well-formed formula. In addition, a formula A in first-order logic is said to be valid, either universally, logically, or absolutely valid, if and only if every interpretation D is a model of A. So this means if every interpretation makes A true, then A is defined to be logically valid. And we denote this simply by models A. Instead of specifying the interpretation, we know that every interpretation makes A true, and so A is logically valid. Okay, so notice that with this new definition of being a valid formula and these new interpretations, we're defining another way to provide semantic meaning or truth values to first-order formulae. So we want to compare our notion of semantic meaning previously in terms of tautology with this new semantic meaning of being universally valid or logically valid. Recall that we define a formula in predicate logic to be a tautology if we strip out all that new meaning, look at its abstraction, and look at how the connectives behave in the old way of defining the semantic meaning. So luckily, if we do all of that and discover that A is a tautology, then it turns out that every interpretation of A will also be true. So if A is a tautology, then it's also valid, which is good. However, on the other hand, being valid and looking at the truth value there is a much stronger property because we're not stripping away the meaning of the quantifiers. We're actually looking at what the meaning of that well-formed formula is within particular interpretation. So within any possible interpretation we have, we define A to be valid if any interpretation makes it true. So this is a strictly stronger property, which means it does not imply that A is a tautology. That added meaning provides additional meaning. So for example, if we consider the well-formed formula x equal to x, we know that no matter what interpretation we have here, the equal sign has particular meaning that always x is equal to x, right? So no matter how we define our domain, whether it's numbers, sets, whatever, equal sign is defined so that x is always equal to x. So that means that this is a universally valid formula. However, it's not a tautology, right? Consider, what is the abstraction of x equal to x? It's simply a Boolean variable p. But there is a state that makes p false, and so that makes this not a tautology, yet it is valid. So this provides us with a stronger sense of how to see truth and to, as you will see, construct even more absolute theorems. Okay, so speaking of absolute theorems, right, remember in propositional logic, soundness and completeness allowed us to connect the meaning of tautology and those semantic truth values with the methods of proofs that we used in our absolute and relative theorems. So now, soundness and completeness within predicate logic involves connecting this new notion of semantics, so this notion of a universally valid formula, with ones that are absolute theorems or relative theorems. So soundness in first order logic says that if A is an absolute theorem, for example, then A is logically valid. So it turns out that everything we can prove is true is really true in predicate logic. We also have Gödel's completeness theorem, which tells us that predicate logic is also complete. So this gives us the opposite direction. So if A is a universally valid formulae, then it can be proven. Okay? Notice that to show something is universally valid is actually quite difficult. It's not really possible to determine if every interpretation makes A true. To consider every possible interpretation is nearly impossible. So this isn't as useful as the completeness of propositional logic, yet Gödel was able to prove that every universally valid formula A can be proven in predicate logic. There's also Gödel's incompleteness theorem, which we may talk about on the last day, but formally for our course, we'll just be sticking with this statement here. Okay, so that completes the video lectures for the course. Thank you very much for engaging in the video lectures. I hope they were helpful, and I hope they help you to prepare for the final exam.